Welcome back, everyone. Ready for another deep dive? Today, we're tackling large language models, specifically how they store and extract knowledge. Like, when you're chatting with one of those AI bots, how do they actually learn and remember things?
That's a great question, and it's something that researchers are really digging into.
Right, and we're going to look at a paper called Physics of Language Models, Part 3.1, Knowledge, Storage, and Extraction.
It's a fascinating paper. Zeyuan Allen-Zhu and Yuanzhi Li, the authors, they really get into this key question. Do LLMs actually learn to extract knowledge from data, like we do when we read, or are they just memorizing answers?
Kind of like cheating on the test.
Exactly. So to figure this out, they used synthetic biography data, which is really clever.
Okay, so they're using fake biographies. What does that look like?
Well, they actually used two different data sets. The first one, called BioS, is totally made up. 100,000 biographies, each with 6 sentences. Each sentence covers a specific thing: birth date, birth city, university, major, employer, and company city.
So it's like a really structured, basic bio.
Yeah, exactly. And then the second data set, BioR, this one's a bit more interesting. They used LLMA, another language model, to actually generate the bios.
Whoa, so AI making bios about AI, that's pretty meta.
Right, and they use the same 6 attributes from BioS as prompts. So it's still controlled, but the language is more natural, closer to what you'd see in the real world.
So they have these bios, and then they train LLMs on them.
Exactly, but they tested two different ways of training: mixed training and then pre-training and then fine-tuning.
Okay, so mixed training first. What's that all about?
So in mixed training, they train the model on both the bios and a set of question-answer pairs, like questions about those individuals in the bios.
And they're trying to see if the model can answer questions about people it hasn't seen specific Q&A pairs for, right?
Yep, they want to see if it can generalize.
Gotcha. And how did that go? Like, did it work?
Actually, yeah, it did. They got some really good results with mixed training, like 86.6% accuracy on BioS and 77.7% on BioR when tested on unseen individuals.
Wow, those are pretty high numbers. So does that mean LLMs are learning like we do?
Well, not so fast. They found something really interesting. The researchers called it abnormal learning behavior. It seems the LLMs weren't actually learning directly from the bios.
What do you mean?
It's like they focused more on the Q&A pairs. They encoded the knowledge from those pairs and then linked it to the bio data.
So they're not understanding the bios as a whole, but more like finding patterns in the questions and answers.
Exactly. It's more about pattern recognition and association than true understanding, at least in this case.
Interesting. So that's mixed training. What about the other method, pre-training and then fine-tuning? How's that different?
So with this method, they first pre-train the model on just the bios. No Q&A pairs yet.
Like feeding it a ton of information and letting it soak it all up.
Exactly. And then in the fine-tuning phase, they introduce a subset of Q&A pairs.
So it's like someone studying a textbook and then taking a quiz.
Yeah, a good analogy, but here's the thing. When they tested this method on unseen individuals, the models did terribly, like almost zero accuracy.
Really? So just reading the biographies wasn't enough.
Nope, not at all. And that's where knowledge augmentation comes in.
Knowledge augmentation, huh? Sounds fancy. Tell me more.
So they tried different ways to improve how the model stored and retrieved info. They looked at 3 specific techniques: multiplicity, permutation, and full name.
Okay, break those down for me. What's multiplicity?
It basically means creating multiple versions of the same bio for each person, using different wording, a sentence structure.
So paraphrasing the same info in different ways. Why would that help?
It gives the model more diverse examples to learn from, helps it generalize better.
Makes sense. What about permutation?
Permutation means mixing up the order of sentences in the bios.
So the birth date might come before the birth city or after the university, like that.
Exactly. By changing the order, you force the model to learn the connections between the facts, not just rely on the sequence.
Okay, I'm getting it. And the last one, full name. What's that about?
This one's pretty straightforward. They replace all pronouns with the person's full name throughout the bio.
So instead of he went to Harvard, it's John Smith went to Harvard all the time. Seems a bit repetitive.
It might seem that way, but it actually reinforces the link between the name and the attributes, makes it easier for the model to extract the knowledge.
So how did these augmentations affect the model's performance? Did they make a difference?
Oh, a huge difference. Each technique helped on its own, but using all 3 together was the real game changer. For example, with BioS, accuracy jumped from a measly 9.7% to a whopping 96.6% using 5 different entries per person.
Wow, from almost failing to acing it. That's incredible. So augmenting the data is clearly super important, but what about those massive data sets? It seems like a lot of work to augment everything.
That's true, and that's why they looked at something called the celebrity effect.
The celebrity effect sounds intriguing. What's that all about?
They wanted to see if augmenting data for just a subset of individuals, like creating celebrities, would help with knowledge extraction for everyone else, the minority group.
So like having really detailed info about a few people could boost the model's understanding of everyone else, even if their data isn't augmented? And
Exactly.
did it work?
Surprisingly, yes, adding those celebrity bios really helped with knowledge extraction for the minority group, even though their data was still basic.
So maybe we don't need to augment everything, just a select few. That's a pretty cool finding.
Right. But there were some limitations. They found that if the celebrity data was formatted differently from the minority data, the effect wasn't as strong.
So consistency in formatting is key. Makes sense. We've talked a lot about how these bodies store knowledge, but how do we actually see what's going on inside? It's not like we could just peek into their digital brains.
That's true, but researchers have clever ways of probing these models. They use two techniques in this paper: position-based probing, or p-probing, and query-based probing, or q-probing.
Okay, let's start with p-probing. What's that all about?
So with p-probing, they train a linear classifier to predict certain attributes, like birth date or university, based on the model's hidden states at specific points in the bio.
Hidden states.
Yeah, think of it like the model's internal representation of the text. It's how it's processing and understanding the information.
Got it. So they're looking at how the model reacts to different parts of the bio.
Exactly. And what they found is that models trained on augmented data were much better at storing knowledge directly. Like, they could predict attributes even at the very beginning of the bio after just seeing the name.
Whoa, so it's like the model learned that this name is directly linked to these specific attributes, no matter where they appear in the text.
Exactly. It's like having a mental index that says this name equals these facts. But the models trained without augmentation, they needed more context. They had to see more of the bio to make accurate predictions.
So augmentation helps the model create a more direct and efficient connection between names and their attributes.
Precisely. It's not just about memorizing more, it's about organizing the information in a way that makes it easier to access.
That makes sense. Now, what about the other probing technique, Q-probing? How's that different?
Q-probing is even more focused. Instead of looking at specific points of the bio, they train a classifier to predict attributes based on the final hidden state after giving the model just the person's full name.
So it's like asking the model, okay, you know this name, now tell me everything you know about this person without any other context.
Exactly. And guess what? The models trained on augmented data did much better here too. They were able to extract attributes directly from the name itself without needing any other clues.
So again, augmentation seems to create a stronger and more direct link between the name and its attributes in the model's memory.
Exactly.
Okay, so far we've been talking about models like GPT, which process text sequentially. But what about bidirectional models like BERT, which look at the entire input all at once? Could those models potentially solve some of these knowledge storage issues?
That's a great question, and the researchers tackled that too. They adapted BERT for this task using masked language modeling, or MLM.
Masked language modeling, what's that?
It's where you train the model to predict missing words in a sentence. Like, you give it a sentence with some words blanked out, and it has to figure out what those missing words are.
So kind of like filling in the blanks. Interesting. And did BERT perform better?
The results were a bit mixed. BERT did really well with attributes like birth date and major, which are single words or made up of independent words.
But
But it struggled with attributes like birth city and company city, where the words are more closely related.
why would that be?
It seems like even though BERT looks at the whole sentence, it got hung up on the strong connections between those related words, rather than connecting them back to the person's name. For example, with New York City, it focused more on the New York and city relationship than on linking that whole phrase to the person's name.
So even considering the whole context didn't necessarily fix the problem. Interesting.
Right. So their conclusion was that while MLM, the technique BERT uses, might be less sensitive to the order of information, it doesn't automatically lead to better knowledge storage, especially for more complex attributes.
That's a really important point. It's not just about the model's architecture or how it processes text. It's about how the knowledge is organized and stored within the model.
Exactly. Choosing a more complex model doesn't automatically solve everything. We need to think carefully about the nature of the knowledge itself and how to present it to the model in a way that makes sense.
It's pretty wild to think about, right? Like these models trained on a mix of bios and Q&A pairs, they actually do better on unseen data than those trained just on bios first and then fine-tuned with those questions and answers.
It is a bit counterintuitive. Imagine giving someone a textbook and a stack of flashcards. You'd think they'd learn best by really diving into the textbook first, right? And then using the flashcards to test themselves.
Yeah, that's what I would think, but that's not what this research is showing.
Nope. The researchers dug deeper into this using those probing techniques we talked about to analyze how knowledge is stored and accessed within the models.
Let's get into those techniques then. We've got position-based probing or p-probing and query-based probing or q-probing. Starting with p-probing, can you break it down?
Sure, p-probing is a way to look at what's going on inside the model to see how it represents the information it's learned. Basically, they train a separate linear classifier.
A classifier.
Yeah, like a simple algorithm that tries to predict specific attributes.
Like the birth date or the university attended?
Exactly. And it makes these predictions based on the model's hidden states at particular points in the biography.
Okay, so hidden states. What are those exactly?
Think of them as the model's internal representation of the text, like its understanding of the information as it processes it. It's a bit abstract, I know.
Yeah, a little bit. So they're using this classifier to see how the model reacts to different parts of the bio.
Exactly. And here's the interesting part. They found a big difference between models trained with and without data augmentation. The models trained on the augmented data, those were much better at storing knowledge directly.
What do you mean by directly?
Well, they could predict those attributes accurately even when they only looked at the hidden states from the very beginning of the biography.
So, like after only seeing the person's name.
Yep. It's like the model learned that this name is directly connected to these attributes no matter where those attributes appear in the text, like a mental index that says this name, these facts.
Pretty efficient, huh?
Yeah, very efficient. But the models trained without the augmentation, they needed more context. They had to see more of the bio to make accurate predictions.
So it seems like augmentation really helps the model build a more direct link between those names and attributes, right?
Right. It's not just about memorizing more data. It's about organizing that information in a way that makes it easier to access.
Makes sense. Now, what about that other probing technique, the Q-probing? What's that all about?
Hue probing takes this idea even further. Instead of looking at those hidden states at different points in the bio, they train a classifier to predict the attributes based on the final hidden state. But get this, they only give the model the person's full name.
So they strip away all the other biographical information and just see if the model can make those predictions based on the name alone.
Precisely. It's like saying to the model, okay, you've seen this name before, now tell me what you know about this person without any other hints.
And how did that go?
Well, guess what? The models trained on the augmented data, they aced it. They were much more accurate in predicting the attributes from just the name itself.
Again, suggesting that the augmentation really helps solidify that connection between the name and the attributes in the model's memory, right?
Exactly.
Okay, so we've talked about these sequential models like GPT, which go through the text step by step. But what about those bidirectional models like BERT? They consider the entire input all at once, right? Do they handle this knowledge storage stuff any differently?
The researchers actually looked at that too. They adapted BERT to tackle the same task, and they did it using masked language modeling, or MLM.
I've heard of MLM, but I don't really understand it.
Well, it's actually pretty intuitive. You basically train the model to predict missing words in a sentence. Like, you give it a sentence where some words are blanked out, and it has to figure out what goes in those blanks.
Oh, okay, so it's like a super advanced fill-in-the-blank exercise.
Exactly, and they wanted to see how BERT would perform using this MLM technique. Would it be better at storing and extracting knowledge?
And what did they find?
Well, it was a bit of a mixed bag. BERT was great at those simple attributes, like the birth date and the major, the ones that are either a single word or made up of independent words.
Okay, but it struggled with something, right?
Yeah, it struggled with those more complex attributes like birth city and company city, the ones where the words are really closely related.
Why would that be? It seems like being able to see the whole sentence at once would be an advantage.
You would think so, but it seems that even with the full context, BERT got a little too focused on the strong relationships between those closely related words. Like, instead of connecting the whole phrase back to the person's name, it got caught up in the individual word connections within the phrase itself.
Can you give me an example?
Sure. Let's say the phrase is New York City. Instead of linking that whole phrase to the person's name, it focused more on the New York and City connection.
So it's like it was paying more attention to the grammar than the meaning?
In a way, yes, and that's why it struggled to accurately extract those more complex attributes.
So even though BERT considers the entire sentence, it's still not a perfect solution for knowledge storage.
Right. What they concluded was that MLM, this technique that BERT uses, might be less sensitive to the order of the information, but it doesn't automatically lead to ideal knowledge storage, especially when you're dealing with those attributes that have a lot of internal word dependencies.
That's a really important point. It's not just about the model's architecture, whether it's sequential or bidirectional. It's also about how that knowledge is organized within the model itself.
Exactly. Choosing a more complex model doesn't automatically fix all the problems. We need to think carefully about how that knowledge is represented and presented to the model if we want it to be effective at storing and retrieving information.
That makes a lot of sense. So, knowing all this, what can we do to actually improve the way LLMs handle knowledge? What did the researchers suggest?
Well, based on their findings, they made two key recommendations.
Okay, lay 'em on me.
First, they emphasize the importance of focusing on rewriting and augmenting the pre-training data. They're saying that simply feeding the model a ton of raw, unprocessed data isn't enough.
Okay, so quality over quantity, basically.
Exactly. They suggest really carefully rewriting and augmenting the data, especially for those pieces of information that are rare but really important. And they specifically recommend those techniques we talked about earlier: multiplicity, permutation, and full name.
So basically, be more strategic about the data you feed the model, right?
Right. And their second recommendation is to incorporate that instruction fine-tuned data earlier in the training process.
So those question and answer pairs we talked about.
Yep. Traditionally, those are introduced during the fine-tuning phase after the model has already been pre-trained on a massive data set. But they're suggesting we start introducing those types of examples earlier on.
Why would that make a difference?
Well, they think it could help the model learn how to use the knowledge it's acquiring more effectively. It's like giving it more practice along the way, rather than just throwing it all at once at the end.
So it's not just about the data itself, it's about how and when you present it to the model.
Exactly. They're advocating for a more integrated and holistic approach to training. Instead of treating knowledge acquisition and knowledge utilization as separate stages, they're suggesting we start blending them together earlier on.
So it's not just about building bigger and bigger models, it's about being smarter about how we teach them.
Exactly. This paper really highlights that. It's not just about scale, it's about strategy.
And it all comes back to knowledge, right? How these models acquire it, store it, and then actually use it. It's like we've been focused on building a massive library, but we haven't spent enough time thinking about the cataloging system.
A perfect analogy. We need to make sure that knowledge is organized and accessible, or what's the point of having it?
Exactly. Well, this has been an incredible deep dive. We've learned so much about how LLMs store and use knowledge, and it's clear that there's still so much more to explore.
Absolutely. This field is moving so quickly, and there are always new discoveries being made.
It's exciting to think about what the future holds for these models and how they might continue to evolve.
I think we're just scratching the surface of what's possible, and as we learn more about how these models work, we can create even more powerful and sophisticated AI systems.
I can't wait to see what's next. But for now, thanks for joining us on this deep dive into the world of LLMs and knowledge.
Until next time.